In previous lectures, we have seen the interfacing of output devices like LED, 7-segment display and LCD. Now we are going to see the interfacing of input devices. For input devices, we are going to see ADC and keyboard. Here I am. Remember the course objectives. Understand the principles of interfacing, and today we are going to see ADC. ADC is analog to digital converter. Analog signals are continuous with infinite values in a given range. Digital signals have discrete values such as on, off or 0 and 1. So what are the limitations of analog signals? Analog signals pick up noise as they are being amplified. Next, analog signals are difficult to store. Analog systems are more expensive in relation to the digital system. Over to this, what are the advantages of digital systems? Noise can be reduced by converting analog signals in zeros and ones. Binary signals of zeros and ones can be easily stored in memory. Technology of fabrication digital system has become so advanced that they can be produced at low cost. So devices are of low cost. The major limitation of digital system is how accurately it represents the analog signal after the conversion. So here is the analog to digital conversion. We have seen what is analog signal, what is digital signal, and how digital signal is advantageous over analog signal. So let us have analog to digital signal, because whatever the data we are getting from the sensors, transducer, we do have in the analog form. So for analog to digital conversion, we will be going for the ADC, that is analog to digital converter. Let us understand the importance of the ADC. This is the digital data acquisition system. Starting from the taking the signal. Signal is available in the physical form. It is converted into the electrical form by means of the transducer or sensors, which includes the noise. So for this we go for the signal conditioning. With signal conditioning, noise is little bit reduced and the current signal is amplified. Next, we want this signal in the digital form. That's why we are going for analog to digital convert. Once we have this data in digital form, we can process it with the computer or microcontroller. So here is the importance of this ADC. Next, let us understand little bit in depth about ADC. A typical ADC circuit with one analog input signal and 3 digital output lines with 8 possible line combination, that is 0, 0, 0 to 1, 1. So 1:3. Okay, and 2:3 gives us 8 possible symbols starting from 0, 0, 0 to 1, 1, 1. The graph of the digital output of corresponding analog input is shown over here. Here you can see this is the analog signal which is shown with respect to full scale. Okay, 4/8 of the full scale, 2/8 of the full scale, and 8 of 8, that is the full scale voltage. And here is the corresponding the digital signal. Let us summarize this A to D conversion. Maximum value this quantization process reaches is 7/8. 7/8 is the maximum value we are getting out of this for a 1 volt analog signal, which includes this 1/8 as an inherent error. This 1/8 volt, an inherent error, is also equal to the value of least significant bit, LSB, that is the 001. Next important terminology is resolution. resolution of converter is defined in terms of the number of discrete values it can produce. Also, it is expressed in number of bits used for conversion, or as 1 upon 2 raised to n, where n is the number of bits. So higher is the number of bits, more is the resolution, because smaller is the step size, lower will be the quantization error. So it is always encouraged, higher is the number of bits of the ADC, smaller with the step size, and more accurate conversion we will get. So here is the definition of resolution. The value of most significant bit MSB is 100 is equal to half the full scale voltage value. The value of the largest digital number 111 is equal to the full scale value, means full scale value minus the LSB, that is this 7/8. The quantization error can be reduced or resolution can be improved by increasing the number of bits used for the conversion. We have discussed it here only. More are the number of bits this n, smaller will be the step size, lesser will be the quantization error, and more accuracy will be there for the conversion from analog to digital. So these are the some basics of the ADC that we need to understand. Let us understand it more with one suitable example. Assume the input analog voltage is changing between 0 to 5. Calculate the resolution. What is the maximum possible voltage out, that is the full scale voltage. If the output voltage is 1000, what is the input? Let us assume the input voltage is between 0 to 5. How resolution is calculated? 1 upon 2 raised to n. N, it is the 8 bit. 4 and 4, 8 bit are there. That's why it is 2 raised to 8. So 9.53 millivolt we are getting per step. What is the maximum possible voltage out? It will be the called as the full scale. So it is ranges from 0 to 5. So it is the phi is the maximum possible voltage out. If the output voltage is 1000, input will be maximum voltage divided by 2. So maximum voltage is phi in our case, divided by 2. So 2.5 will be the output voltage for this, because this is nothing but the MSB. We have seen in previous concept, MSB is nothing but what? Full scale voltage divided by 2. So this is nothing but the value of MSB. Here let us assume that input analog voltage is changing between -5 to +5 voltage using 10 bit ADC. Calculate the number of quantization levels. Calculate the voltage resolution. Assume the input voltage is changing between -5 to +5. So to calculate the number of quantization level, it will be 2 raised to 10, as our ADC is 10 bit. N is equal to 10 here, that's why quantization level will be 2 raised to n, that is the 2 raised to 10. Calculating the voltage resolution, input voltage divided by 2 raised to n. So input voltage is 5 minus 5, the range is -5 to +5. So it is 10 volt divided by 2 raised to 10, that is 1024, and we get 9.76 millivolt. Let us understand ADC 0809. This is the one example IC we are going to see to understand the ADC. This is an 8 analog input channels are multiplexed and selected according to the table we are going to see. So this is the 8 channel input ADC. We are having the IN 0 to IN 7, 8 channel to the ADC. So we can take 8 analog data into the ADC for conversion, connected at different channels starting from 0 to 7. So that's why it is called as the 8 channel ADC, having 8 channels for taking input. So channel is selected based on this select line A, B, C. Let us see how to select the channel using this select line A, B, C. Here is the table A, B, C. Understand, A is the LSB. Take care while selecting the channel. Note that A is LSB. So to select IN0, the bit position of channel A, B, C should be 0, 0, 0. Then channel 0 will be selected. With bit position 1, 0, 0 or 0, 0, 1, channel 1 will be selected, and likewise to select channel 7, all the bits we will be making 1, then channel 7 will be selected. So wherever you are connecting your analog input, select that particular channel by making this particular bits 1 or 0 according to the channel we are going to select. So this is 8 bit ADC, or having 8 analog inputs, 5 volt supply, 0 to 5 input volt range will be there, 8 bit data output which is TTL compatible, so that we can easily interface it with the microcontroller. Low conversion time, that is of 100 microsecond only. 8 bit resolution. Hope you understand now what is 8 bit resolution. 2 raised to n. High speed and high accuracy. So speed of ADC is based on the conversion time and the accuracy is based on the resolution. So this both points are of worth important, that to consider the speed and the accuracy of any ADC. And at the last, it is having low power consumption, that is less than 15 milliwatt. How to calculate the step size? It is based on the V in and the n bit ADC, that is the number of input channels. So step size is calculated as V in upon 2 raised to n. So step size depends on two factors. First, V in. Here is the table that we can understand the V in, and V in is depend on the V reference as shown over here. If V reference is not connected, by default it is connected to 5 volt supply. So when V reference is not connected to any voltage source, V in will be in the range of 0 to VCC, whatever VCC we are giving, but natural VCC is 5 volt over here, so input will be within the range 0 to 5 volt. And how the step size is calculated? V in divided by R is the 8 channel ADC, 2 raised to 8 will give the 256. So 5 upon 256 will be 19.53. Now in this case, when V reference is given 2.56, see, V reference is 4 volt, then V in will be 0 to 4. For this case 2.56, here you can see, if V reference is connected to 2.56, V in will be ranging from 0 to 2.56 and the step size will be 2.56 upon 256, that is 2 raised to 8, will give us the step size of 10 millivolt. So lower is the V reference, lower is the step size. Lower is the step size, higher is the accuracy. So this is the second factor on which this step size is depend, the n bit, the factor at denominator. Here we have seen the factor at numerator of this formula V in. How this n affects the step size, here we can understand. If it is 8 bit ADC, number of steps 2 raised to 8, 256, 5 upon 256 we get this. For 10 bit ADC, 2 raised to 10, 1024, so we will be getting the step size 4. So higher is the number of bits, lower is the step size. Lower is the step size, higher is the resolution and accuracy. So step size or resolution is the smallest change that we can discussed by an ADC. So here is the importance of this step size. Now let us see how to program an ADC. First, we have to select an analog channel by providing bits A, B and C. We have seen the table how to select the channel. Once we have selected the particular channel, activate ALE pin by giving low to high pulse and or making it high, indicating that whatever channel we have selected, ADC will latch the address of that address and will be considered for taking the input. Second, once the channel is fixed, microcontroller is telling ADC for starting the conversion. It requests ADC for starting the conversion by giving high to low pulse or making the particular pin high. Then internally ADC starts the conversion. We have to wait for the end of conversion. Microcontroller will come to know about end of conversion by monitoring this EOC pin. When this pin goes high, it will confirm that conversion is completed and next we have to take the data. So once microcontroller knows that EOC has gone high, indicating there is end of conversion from ADC, then microcontroller requests ADC to give the data by activating this OE pin, output enable. How it is activated? By an high to low pulse to the OE pin will bring the digital data out of the chip, which will be available at D0 to D7 pin of the ADC. So next we have to take that data into the computer or into the microcontroller. Here we can understand the hardware description and the pin involved in the interfacing. Here are the pins of 8051, whether it is configured as input or output, and pin of ADC. So this is ADC side, this is 8051 side. So we will be using port 1 of 8051 to collect the data. So here D0 to D7 pin of the ADC will be connected to P1.0 to P1.7. P2.4 will be configured as output. We will be making this ALE signal high. Here this port should be configured as an input port as we are taking the converted data out of the ADC. So here should be the input written. P2.4 will be ALE. We are activating ALE signal to latch the channel. P2.7 we are taking as the input because it is giving the signal from ADC to 8051 that conversion has been taken place. So pin 2.0, 2.1 and 2.3 will be used for channel selection. It will be connected to the pin A, B, C of the ADC, which is used for the channel selection. Next P2.5. P2.5 will be the output pin. With this pin we are giving signal to ADC that give the converted data, that is the OE, output enable. P2.6 will also configured as an output, that we are giving signal from microcontroller to ADC. It is the signal requesting ADC for the start of conversion. So in this way, here are the pins from microcontroller side, these are the pins from ADC side, and this will be status. Only P1.0 to P1.7, that is port 1 pins, and P2.7 pin are configured as an input pin, and rest of the pins will be configured as an output pin. Let us understand this communication between the ADC and microcontroller with this timing diagram. This is called as the timing diagram. Everything happens with respect to clock. So let us understand how the communication from microcontroller to ADC is taken place. Initially, Microcontroller selects the channel by giving the address to ABC. Once channel is selected, this channel is latched in the ADC by giving this high signal to ALE. Next, microcontroller requests ADC to start the conversion by making this particular pin high. That is start of conversion. So here, after latching the channel, request is sent from microcontroller to ADC to start the conversion. Then we have to wait for the EOC, end of conversion. So when we come to know about the end of conversion, here we come to know about the end of conversion when this particular signal goes high. Next, we have to give signal from microcontroller to ADC, that is it is the request, whatever converted data that will be get available of the D0 to D7 pin of the ADC, and once that data is available, after giving OE, available data at D0 to D7 pin of the ADC will be taken from microcontroller. In this way, the communication between the ADC and microcontroller takes place during the analog to digital conversion. Let us understand the program. Here is the actual interfacing of the ADC and 8051. Whatever hardware we have described previously is the same. Port 1 is engaged in D0 to D7 for taking the converted data from ADC to microcontroller. This P2.5 will be given the request to enable the converted data for collection. P2.6 give the signal for start of conversion. Channel will be selected from this P2.0, P2.1 and P2.2. Once the channel is selected, this address is latched with this ALE pin. Then start of conversion, wait for the end of conversion with this INTR pin. This gives the end of conversion signal by making this pin high. So we are going to monitor this P2.7 whether it becomes high. And once the conversion is completed by this signal, microcontroller will request to ADC, please output the converted data on D0 to D7 pin. Make the converted data available on D0 to D7 pin. So after making this OE enable, this converted data will be available on D0 to D7 and microcontroller will be taking that data into the port P1. So same way we are going to write in terms of the program, in terms of the assembly language instruction. Starting address of the program, make the port 2 as an output port because we are using the port 2 bits for giving the output signal from microcontroller to ADC. Port 1 is configured as an input port because we are from here we are getting the converted data from ADC to into the microcontroller 8051. After that, we are configuring P2.7 pin as an input pin because we want to read the status of this pin whether it has gone high or not. So this is the configuration of the ports. Next is the selecting of channel. We want to select the channel 1 here. To select the channel 1, what should be the bit position of this ABC? 100. So make this P2.2 high and P2.1 low, P2.0 low. Here it should be P2.2 high, P2.1 low, P2.0 low. So in this way we have selected the channel 1. Next, latch the address by giving high signal to high to low signal, high signal to the ALE. P2.4. P2.4 is connected to ALE, so high signal is given to the ALE. After that, start of conversion. Start of conversion P2.6. So how? By giving the high to low pulse here. Set B P2.6, CLR P2.6. So by giving high to low pulse, the start of conversion starts. With JB P2.7, here we have to read the status of this INTR pin, which is nothing but the P2.7. It should go high to low. That's why we are first ensuring the bit is high, then we are ensuring the bit is low. So when this bit completely goes high to low, we ensure that there is end of conversion. When the conversion is end, we have to request ADC for giving that converted data by making this OE its RD bar, active low signal. So make this pin low, that is CLR P2.5. So with this we are requesting ADC to send the converted data. Then ADC makes that converted data available on this D0 to D7 pin. Then role of microcontroller is to collect that data from the port to the accumulator. So that's why we have written move A, P1. And from accumulator we can display it on the another port, send it to the port 0. Next we are clearing read signal for next round. Every time we have to request ADC for getting the data after conversion. In this way we are doing it continuously to get the data from this channel 1. So in this way the ADC conversion takes place and the communication between the ADC and Phi 1 takes place while doing the ADC. So this is all about the analog to digital conversion. These are the possible questions.